So at this point, what I want to do is I'm going to stop and do a couple of practice problems using these relationships between energy and energy of a photon and the wavelength of light. And so the first one is a pretty direct problem where we have a light source. So this is the laser that's used in a Blu-ray player. And it has a wavelength around 405 nanometers. As you might recall from our electromagnetic spectrum, this is going to be in the blue-violet, right? It's going to be at the very edge of the visible spectrum. And we want to know what the energy of one photon of this this wavelength of light will be. So, of course, our equation here is going to be that the energy of a photon equals h times the frequency, or it might be more convenient for us here to use it in terms of the wavelength because the wavelength is directly given to us. So that energy also equals hc over the wavelength. Now, if we remember from our other problem, right, when we're working with anything that has to do with these kinds of problems, we need the wavelength in meters. So let's go ahead and put 405 nanometers into meters. And so remember, if I have 4.05 nanometers, remember that 1 nanometer is 1 times 10 to the minus 9th meters. And so if we do that math, we get 4.05 times 10 to the minus 7th meters. Okay. So this is something that you're going to be doing quite often, and you need to always remember that often we're given wavelength in other units like nanometers, but we do calculations, we need to have it in meters. Okay, so now that we know it in meters, we can go ahead and use our equation. So the energy of a photon is going to be equal to hc over lambda. So remember, h is 6.626 times 10 to the negative 34th, and that's in units of joules seconds. And speed of light, 3 times 10 to the 8th meters per second, divided by our wavelength, 4.05 times 10 to the minus 7th meters. Now, we have meters here, they're going to cancel. Now, also know that we have times seconds divided by seconds, those are going to cancel, and we're going to be left with units of joules, or our classic energy unit. So if we do this, we get, if we do the top here, we get 1.988 times 10 to the negative 25 joules. Again, divided by 4.05 times 10 to the minus 7. I've already canceled my units. And if we do that, we get the energy of a single photon is going to be equal to 4.91 times 10 to the minus 19 joules. Now, a couple things to point out. Notice this is a really small value of energy, right? But what we have to remember is it's just one photon of light. And so it's going to be a relatively small amount of energy. Now, while we think about the photoelectric effect as, in order to get those electrons emitted, right, this energy of the single photon has to be right. But if we're using a light source to shine on something, right, that energy does have an additive effect. So, I mean, when we give off, say, a pulse of light or a beam of light, right, it contains a whole bunch of photons. And those photons together, right, might be a substantial amount of energy. So this is the energy of a single photon of light. Now, if we look at the next problem, this is a little bit more complex. Here we have another kind of laser, right? And we get a laser pulse. The wavelength of this laser is 330 nanometers. And the pulse has a total energy of 383 millijoules. And we want to know how many photons does that pulse contain to give you that total amount of energy. So, how are we going to calculate the number of photons, right? So, if we think about it, the number of photons is going to be equal to the total energy, right? In other words, this 383 millijoules divided by the energy of a photon. So if we take the total energy divided by the energy of a single photon, that's going to tell us the number of photons. So that's basically what we need. We need the total energy and we need the energy of a single photon. Okay, so what do we know? Well, we already know the total energy. Now, the key here is, right, we want to be in units of joules, because we see from up here that, you know, when we talk about energy of photons, we're going to do in joules. So first thing we need to do is probably convert this into joules. So if I look at that, 3.83 millijoules. I'm remembering my metric system, right? 1 millijoule, 1 times 10 to the minus 3 joules. And so 3.83 millijoules sorry, 383 millijoules is equal to 0.383 joules. So that's the total amount of energy we emitted. Now, next we want to calculate the energy of a single photon. So here we did that up here, right? So we're going to do the same thing we did up here. Right? We're going to use hc over lambda because we have the wavelength. Now, I'm not going to do the units conversion, but remember what we did up here. And what we should see is that 330 nanometers is 3.3 times 10 to the minus 7 meters. And so if I go ahead and write this out, so I'm going to have HC, so 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 8th meters per second divided by 3.30 times 10 to the minus 7 meters. And again, my meters cancel, my seconds cancel, and we're going to end up with energy units. So energy of the photon equals here 6.02 times 10 to the minus 19 joules. So we have the energy of a single photon here. We have our total energy here. So now we can calculate the number of photons as 0.383 joules divided by 6.022 times 10 to the minus 19 joules. And we get that we have 6.36 times 10 to the 17 photons. So while each photon has a really small energy, right? If we use a lot of photons, we can get up to a reasonable amount of energy, right? So it takes a lot of photons to get up to sort of energies on the scale of joules. Okay, so this was a couple problems working with these equations that interrelate the energy of a photon to the wavelength and the frequency. So next time we'll be talking about atomic emission spectrum.